Okay, good afternoon all and Happy New Year to all. Welcome to our WMG Group Colloquium. Today it's my pleasure to introduce our speaker, Professor Cameron Pleydell-Pearce from Swansea University. Um, Cameron holds a Tata Steel Chair Professorship in Steel Processing at Swansea University, UK. He is the director of the Sustain EPSRC Future Steel Manufacturing Research Hub and a co-investigator for the TFI Network Plus. His research centers around the foundation industry, specifically in the metal sector, where his key goal is to support and deliver the cutting-edge science and engineering research required to create carbon-neutral, resource-efficient UK steel supply chains. Cameroon holds a long history of interfacing with industry and has a significant experience of managing industry academic research collaborations and relationships. Cameroon is going to present some surprise talk on steel related, so I don't have the topic to present you. But yeah, Cameroon, thanks a lot for taking the time, and the floor is yours now.
I'm sure, as most of you are aware, the global steel use continues on a fairly precipitous upward trajectory until very recently, where the growth in production levels, particularly in China, has started to slow, and that's delivered a level of pain for the industry as it readjusts to that potential over capacity flooding the market in other areas. But generally, of course, we've been on this sort of wild ride of upward trajectory in terms of the not only the production but also the demand for steel. And as we move into a transition to new technologies, we're going to continue to need steel as we embark on a whole series of very large infrastructure projects and to support new technologies to deliver the green transition as well. In the UK, and that means that we're going to have a very sort of stable demand for this material into the future. There are, of course, then on the back of that, industrial developments. So I've picked out, obviously, the very well publicised transformation of the Port Talbot Steel Works from an integrated steelmaking operation to an EAF-based steelmaking operation. And I think those of us who work closely with the industry also recognise that these sorts of transformations have been occurring in a lot of other jurisdictions well ahead of the UK, particularly the US. And we just picked out an image here of the Big River site as one potential example. But I hope to talk about a little bit through the course about how they're leading in terms of time, but there are also potentially some mistakes that they've made in that jurisdiction that we probably don't want to repeat for the UK. But nevertheless, these industrial developments are now happening extremely rapidly, particularly within the UK. And that's an interesting position for us all to be in. One of the things that I've always said is there's never been a more exciting time to work with the steel industry. And there are a lot of opportunities for people to get involved and contribute to the success of that. Lots and lots of fundamental scientific challenges along the way. This is an image that I took from my office of the Port Talbot Steelworks. This is not a sunset, but in fact a sunrise. This is obviously before we ceased iron making operations at Port Talbot, as you can sort of still see the stacks operating there. And my heart, as well as my career, is very, very close to the success of the steel industry in the UK. So this might seem a little dry, but trust me, I will get onto some science in a bit. There is a policy or regulatory context for the work that we work in as well. So we've got the thing around the demands, we've got the thing around the industrial transformation, but we've also got a whole series of things that are going to be introduced in the UK, yes, but probably most importantly within the EU as one of our major trading partners, that are going to have an effect and change the behaviour of some of the UK-based steelmaking operations and the companies in terms of how they perform. And some of those will probably have impacts well beyond the UK and EU jurisdictions as well, with regards to people who might want to import into our area. And one of those examples is the CBAM, which is short for Carbon Border Adjustment Mechanism. So that's a essentially a trade remedy that looks at the carbon footprint of imported materials and then penalizes people if they're producing materials in a very carbon intensive way. And it's trying to prevent what's called the offshoring of carbon, where we deindustrialize the UK in favour of importing carbon-intensive products and materials from other jurisdictions. So that's coming along, and that's going to the thinking is that that's going to reshore supply of material within the UK. Scrap policy is changing internationally significantly. So the UK is now probably one of the only jurisdictions which is now still healthily exporting very, very large volumes of scrap with no other controls in place at the moment. And a good example of this is the waste shipment regulation. That's what WSR stands for in the EU. There's an increased focus on, I've put in brackets that in commas there, critical minerals through things like, you can look this up, but the recent Minerals Security Partnership. In most cases, that's talking about things like battery precursors, cobalt, nickel, lithium, things like that. But you know, you could argue on the basis of those definitions of criticality that things like steel scrap or low embodied carbon steel could potentially fall into that category at some point in the future. And the European Commission is even actually starting to think about discussing that. And those are already starting to result in legislation that's starting to restrict the flow of those materials, so that becomes relevant. From the procurement perspective, we've got product passports were coming in. So the batteries one is the one that's the most advanced within the European Commission, but there are also now significant strides moving forward on how to apply similar passports for construction products, which is a significantly larger, more complex and more impactful potential implementation of product passports. There will be some standardization on the way beyond the ISO standards that already exist for life cycle analysis on emissions reporting and what are called environmental product declarations, EPDs. And there is an ongoing discussion around what the product standards for steel might be, and everybody likes to talk about green steel, but what does that actually mean when you start to report that as a carbon footprint or as a function of the precursors or the input materials that go into that? So all of these things are going to start to change the behaviour of steel makers within the UK, and different jurisdictions have to manage that in their own way. They're managing that through the implementation of strategies. So I've been involved in the development of strategies at the regional level. That could be at sort of the council or combined authority level. And that involves their own innovation and growth plans. There is devolved, so I work closely, as you might imagine, being in Wales with the Welsh Government, devolved strategies. So one is Beyond Recycling, which is the circular economy strategy for the Welsh Government. And of course, within the UK, then we also have national strategies, which are forthcoming and welcome, because we haven't had one for such a long time. But we will also have, and this is the critical thing, the UK Steel Strategy. I thought I would just frame my talk in the context of this, because the UK Steel Council was recently reformulated and met this week. And the steel strategy will be completed by April, and I thought that deserved a sort of eek emoji, because to me that sounds like an incredibly complicated and detailed piece of work that needs to be completed extremely quickly. Obviously, people have been thinking about this for a long time. And what I thought I'd do is I'd give you a sneaky peek, having been involved in some of the prioritization and the development of things that might be going forward for the steel strategy, is to give you an indication of what that might look like. So there will be some subgroups which are developed, which will include some of us in the academic sphere, but also, of course, a whole range of other stakeholders from the industry and government. And they will be looking at things such as, and I'm calling this indicative because I don't believe this has been published or finalised, procurement. So that's looking at the whole supply chain for steel and how do we produce the products that customers need in the future. Raw materials, so particularly a focus on scrap, but also let's call them iron units, which could be DRI, or it could be pig iron, or it could be granulated iron, or the ore itself, of course. Energy, so yes, availability, but critically what vectors we're going to use. So there is a clear move towards electrification within the UK, but we also need to consider the chemical vectors, and we're displacing a huge amount of chemical energy with electrical energy by moving from a integrated steelmaking process to an EAF process. There will be a focus on decarbonisation. They're particularly interested in measurement, and we referred to EPDs and LCA earlier on, but also those new technologies, which we will have a strong hand as academics and innovators in developing. And then they're also interested in trade, and then that might seem almost totally dissolved from the academic sphere, particularly those of us who work in the materials area, but actually monitoring and modelling the flows of materials and assessing those is going to be really, really important information on which they will be able to make some of those decisions. There is another thing on there which I think really should be in there, but so far I haven't seen much evidence on, and that'll be my little bit my sort of reveal towards the end of my talk, hoping that I get there roughly on time. Prakash will keep me on a short leash, I'm sure. So this is the sort of the context. And so what I wanted to think about was, well, if we look at these things of procurement, raw materials, energy, decarbonisation, what is it that we're doing in the academic sphere that's going to be able to contribute to that, and how will it fit in with whatever this published steel strategy happens to be? And we'll find out very, very soon. So I'm going to draw on my experience of leading the SUSTAIN network. I'm very keen on pointing out that it is a network, so it stands for Strategic University Steel Technology and Innovation Network. And I've always been very, very focused on making sure that we bring together as many different players across the academic sphere as possible in joining this, and we continue to grow the partnership through new funding calls and things like this. So this is kind of what it looked like to start, but we've now engaged through a whole series of networking events and funding calls with a whole series of different other universities across the UK who have got valuable contributions to make inside this space. To give you an idea of how we're doing that, we continue to fund new partners. We've just awarded, I think, 3 new feasibility studies. I'm going to struggle to remember exactly where they were funded off the top of my head because it's literally hot off the press, and perhaps I shouldn't announce it here, but we've just funded 3 new feasibility studies, 2 of which I know sit with new partners and new universities that we haven't worked with before within the SUSTAIN network. We have, and this is one of the things I'm most proud about within SUSTAIN, an early career researcher call, which is specifically to fund researchers who are not eligible to apply for EPSRC funding under other circumstances. And we have a whole series of applications which are currently under review. We completed the interviews for those, kind of similar to a fellowship process at the end of last year. And we also have a technology transfer fund, which anybody who has received any form of sustained funding in the past, and there could be those people on the call, can pitch into to try and look at how they might be able to demonstrate the opportunities to take forward some of their work with industrial partners. And any more information on all of this can be found here in calls, and you'll see what we've got coming up in the future. The research within SUSTAIN sits under 2 grand challenge research areas, one of carbon neutral iron and steel making and one of smart steel processing. The idea being that this one delivers a sustainable foundation on which we can grow an industry, and this one is about how we ensure competitiveness across that. And of course, we have a relatively fluid transfer of different ideas across these. This is actually an infographic which is associated with the second half of our program, but we did have a series of tasks, obviously starting 1 to 9 from the first half of the project, and the details on all of those things can be found within the website. And these individual technology areas are underpinned by some carbon counting activity that's being done at Sheffield University, where we look at trying to measure the environmental benefit of each one of these different interactions. So that's what I know. It's not the limit of everything that's going on in the UK by any stretch of the imagination, but I thought I would look at what I know and draw on some things there which might provide some impetus or some inspiration on how we might be able to contribute to this successfully delivering this future steel strategy within the UK. So thinking about procurement, so I thought about that from the perspective of sustainable metallurgy. So Yes, there is a view within government that we need to make sure that more businesses within the UK buy more British steel, and we need to incentivise them to do that on the basis of the fact that we should be producing, and again, this is a difficult definition, greener steel within the UK than perhaps some of our competitors once we've transformed the industry. That is really dependent on ensuring, of course, at a fundamental or at a scientific level, that we're delivering the properties for those steel products that the customers actually want. So there's no point in forcing them to buy something terrible simply because it's from the UK. We also need to make sure that we're competitive and we're developing these high value products. So there's a lot of people within the Sustain Partnership who are working that, many of whom are within the WMG team themselves and some within Sheffield as well. And I do have to apologise that some of these slides might not necessarily be entirely up to date. And so if you don't find yourself on these, please don't take that as a slight from my perspective. There's a big challenge associated with sustainable product metallurgy, which is related to the scrap. Now, I want to talk more specifically about the management of scrap a bit later on when we come to talk about raw materials. But just in terms of what this means for products, we have this excellent track record of developing new products within steel. Not more than 5 years ago, the aluminium guys would look over the fence at us and be extremely envious about our ability to produce thousands of fantastic new grades on an ongoing basis, and we've been very, very good within our industry at developing new novel products with increasingly good combinations of, say, for example, mechanical strength and ductility. The problem with that from a steel maker's perspective is that it becomes increasingly difficult to produce, and so we need to invest in new kit that has better control as the control chart shrinks on these more advanced products that then become more difficult to produce. And what we're currently doing with that at the moment is broadly, this isn't true across the entirety of the material flow, but broadly we're chucking this all into a giant pile and then trying to sort out the problem later on. And what that means is that if you start to pull apart those piles, as we have been doing and colleagues within Warwick have been doing as well, then you start to find that it's contaminated with all sorts of different grades of steel used for different making different things. So these thin products, these sheet products over here, and then some of these more engineering steels and rebar and things over there. But also a whole load of things that aren't steel at all, like ceramic materials, soil, clothes, and copper wires, and that one's obviously well known as a problem, that contamination of copper. So what we're doing is we're sending all of these elements back into this process, and the problem is we've been so good at developing these products, we've shrunk this process window, and then when we start to introduce these elements back in, it starts to throw the process into more levels of variation as we get different compositions coming in through the scrap charge, and that means that it makes it more and more difficult to produce these competitive products. This isn't helped by the fact that if you look at some of the scrap specifications that currently exist for the UK, these are them essentially. So they do produce some indicative compositions, but they're generally done by the look of the material itself, and that's kind of how scrap is graded. That's something we need to change, obviously. So we need to stop chucking stuff in a big pile. We need to stop recirculating these elements coming back through the thing, and we need to think more carefully about how we actively manage those resource flows through more knowledge of the materials that we're generating and passing that data through the supply chain. We talked about passports before that might be able to enable reuse, repair and remanufacture of materials, but also to look where we are recycling them and remelting those materials at sending the elements where they need to go. So we take relevant parts, in this case of an auto body, and we know what the compositions of those are, so we send them back to where they need to go. And this basically means that we need to start thinking more carefully about robust and differentiated products. So we've been focusing entirely on differentiated products, and very successfully too, in the recent past, but we need to now understand how we're going to make them robust. And the purpose of that is to open up this control chart. So better management, so we get less variation, but also slightly more robust and easier to produce products that open up this control chart and make life a bit easier. To produce them and handle those subtle variations in chemistry that might be coming through from higher rates of recycling. And this essentially is what we need to do. Now, on this side, let's talk about sustainable metallurgy. There is some work which you guys are doing. So again, I'm not here to talk about any of the individual research areas in detail, but I just want to draw your attention to what you're doing and how important it is. So this is some work looking at austenite conditioning and some fairly conventional flow stress changes as a function of different levels of contamination. So if we start to contaminate materials more, then we start to get lower fractions of softening, so higher recrystallization temperatures, and that makes the design of the alloys change as a function of different levels of contamination through different residuals. And I know that there's work going on within the Sustain group at the moment, which is looking at how you might be able to reconstruct that austenite grain structure. So using things like EBSD and the orientation relationships that exist through EBSD to be able to recharacterize those austenite grain structures and start to define or correlate some of the observations that we're seeing with regards to changes in the recrystallization behavior as a function of different contaminants in the steel with the structure of those grains. And so this and any of the work that you're doing in this area that's looking at these changes as a function of composition, changes in composition for copper, nickel, tin, or chrome in particular are going to be extremely valuable. So this is one way that you can look to address this. The other way, which has been used a lot in the past, of course, is by looking at these high nickel model alloys that maintain austenite structures. And this is some work that Carlo, I think, is on the call, has been looking at with his colleagues at WMG, where we're looking at how different strain distributions exist for different recrystallization temperatures, and thinking about and conditions, and thinking about how those will change as a function of different contaminations. So all of this stuff fits very neatly into the case for changes in procurement, and that's backed up then by looking at the opportunities to simulate microstructures, look at the grain size distributions that are popping out as a result of those different microstructures, and bringing that all together. Other work that you guys are doing in WMG that's very relevant to this, of course, and you'll be familiar with this, but I'm just talking about the context here. Sorry, I seem to have pixelated Fanfu there, my fault. Is the work around metallurgical sensors. So yes, we are looking at how we can model and understand this change in the metallurgical behavior, but then also you guys are doing a lot of fantastic work looking at how you might be able to validate and measure that behavior through projects that are occurring within Sustain and beyond, funded through the Catapult and other EPSRC projects. Looking at how you can then monitor that on an ongoing basis and then validate the observations that you guys and we collectively in the academic sphere are making on these changes in recrystallization behavior as a function of different residual elements, and actually being able to assess that. So we can use this for the existing portfolio of grades, but this sort of technology is also going to be really important in terms of being able to monitor and actually deliver that. And I'm going to do a bit of scrolling now, which you're not supposed to do in presentations like this, but I'm in charge, so I can, which is going to be really important in terms of opening up this control chart. So one of the things that we can do, of course, is deliver better levels of control on the processes that we implement. And if we can do that, then that gives us this more room for maneuver and gives us this opportunity to produce a wider range of grades with higher recycling rates. And this takes me on to this whole area of performance on demand and process modeling. So there's been an awful lot of work that's been done by so many different well-established groups across the world on process modeling, and particularly physics-based process modeling, looking at, this is solidification structures here, but a whole range of different empirical and physics-based approaches to being able to predict the microstructure or predict the structure property relations or process structure property relations that exist for steel alloys. But increasingly, this is being twinned with a nice word to use, the data fed area. So, and of course, classically, this sort of data driven innovation work over here that is based more on some of those statistical models and what we'll call AI for now, shall we? We're looking at how we can start to join these two fields and look at, for different problems, which are the most effective ways of being able to solve them. So in some cases for process related stuff, which is has large volumes of different potential variables, then it might be more like this. But in some cases, of course, we might find it's just as easy to solve some of these problems with some of the original empirical equations and constitutive equations that we've used to derive relationships in the past. Things like substitutional alloy effects on strengthening, for example. But this bridge between the two and deciding which of these are the best methods is probably going to be really important. So thinking about energy as the next sort of phase of the steel strategy, or one of those subgroups that's going to be really, really important, we can think about this electrical component. Now, this is one of those cases where we're basically looking at modeling an entire plant, the operation of an entire EAF-based steel plant with all of the different processes and intricacies that go on. Now, trying to deal with that from a physics-based perspective is going to be extremely challenging, if not entirely impossible. But some work at Cardiff University has looked at a way of being able to schedule the electrical use. So if we're going to convert to electrical based production, we don't have an infinite supply of electricity in the UK, at least for the time being, and probably for a long time into the future. And so we need to be extremely smart on how we use that. Also, particularly because our prices for electricity are significantly higher than many of our competitors in the global market, including the EU. So we really need to think carefully about how we're going to use that energy, and there is the opportunity, as presented by some of this work that we funded at Cardiff University, to look at digital twins, to do day ahead and intraday scheduling, to look at how we can reduce the demand on the system. And this one specifically was looking at not just the conventional grid as it currently exists now, but the opportunity to fit in more with the potential trends that we might see with residuals, whether the wind is blowing or with renewables, where the wind is blowing or the sun is shining. And so this sort of demonstrates one of those areas where you can think that data-driven approach is really probably one of the only ways that we're going to be able to do this successfully, because it involves lining up a whole series of different processes, each with its own variables and key parameters that need to be managed in order to deliver this optimized demand on the electricity grid. Within Sustain, we're kind of looking at this within a holistic basis as well. So there's some core work within the area looking at a whole series of different things. So the modeling, or the conventional modeling that we're talking about just here. There's some of the life cycle analysis, which I've touched on already at a very high level, and we'll discuss in a little bit more detail later on. And then you've got some of the data that will be maybe coming in through the supply chain and how that might be secured through things like blockchain or distributed ledger technologies. But also considering, and I did see Harry join the call. I was somewhat inspired by a talk that he gave at his best, I think it was his Bessemer lecture, when he had a conversation with an AI, I think during the lecture, which I thought was very inspiring, and that's something that we've been looking at as well. So the opportunities to use what are called semantic technologies. So those are technologies that can, like, think ChatGPT, that can go in and query data on behalf and find a way of making these more human-centric, some of these models. Because I think some of these data-driven models, one of the biggest challenges with them is trust. And we need to be able to see those things working, or be able to interrogate them in ways that are better than they are now, because they currently kind of sit as black box. And the idea is that all of these things will kind of feed together to produce something like materials as a service. So we want better performance on demand. We want better sustainable materials and steel making processes. We want to be able to trace some of the data that exists through the supply chain. And we want then to be able to distribute that data so far as we can across the supply chain, which is going to enable better use of the materials and more efficient use of the material. A large quantity of steel never actually makes it to the final customer through things like machining and forming and such like. But also longer use of those materials, and then the potential to reuse those materials when we get to the end of life. But that's going to be dependent on getting better predictive data and measured data from these advanced sensors to travel with the material through its life cycle. And then that should enable us to make better choices, informed by life cycle analysis on what are genuinely the lowest carbon uses of the material, as well as the lowest carbon production methods of that material. Thinking about the other key variable of energy, it's really that chemical energy. And I alluded at the very beginning to the fact that we are quite bravely, I would say, looking at electrification as the savior of steelmaking, even though the EAF is a far more mature technology than the modern integrated steelmaking. And the big challenge of that is that we're displacing huge volumes of chemical energy in the form of coke, coal, solid carbon, and with electrical energy, which we still have trying to find a way of being able to produce at significant scale. Even if we're able to successfully do that, I think that's possible at the UK level because we're a relatively small player. But if you look at that at the international level, that's going to be a huge challenge. But even if you're able to actually do that, then you need to start thinking about what we're thinking more broadly about the carbon cycle. So we're not just thinking about CO2 as the gas, but we're also thinking about, well, its whole life cycle through the production of solid carbon all the way through to its utilization, combustion, and then potentially catalytic reduction as well, which I'll come on to. So I've stolen this slide from one of our collaborators at Liberty Steel. This is Ed over here. And he presented some work that he'd done analysing what the carbon footprint looks like at Liberty Steel. And I don't forget that Liberty Steel are already an EAF manufacturer within the UK. And you look at the total proportion of the carbon footprint of their materials, and you can see that natural gas makes up over 50% of the total emissions, and that's his scope 2. Okay, so the energy production, but also scope 1 with regards to gases that are used to fire furnaces and such like. About 37% of that comes from electricity, which we might be surprised to see because they're an electrically driven company. And then at around 10% comes from steel making additions. And of those steel making additions, a significant contributor to that is actually the solid carbon that goes into the EAF to help with refining and foaming and control of the composition of the material as well. So so there's actually a significant contribution to the solid carbon to that overall thing, and there's a breakdown of that here where you can kind of look at the impacts of anthracite and the natural gas on the total carbon footprint of the materials. I'm happy to share these slides because I appreciate I'm having to go relatively quickly, but you can have a look at this data at your leisure or review the recording. So so basically, we're still burning a lot of gas even once we completed the transformation to electric steel making, and we're also still using actually quite a lot of solid carbon. And although in total it doesn't make up a significant proportion of such a large total amount of CO2, it makes up a very significant proportion of the CO2 that's generated for EAF produced steels. So we need to think about what alternatives we might be able to use that reduce this, and two options that are being looked at by this is Peter Holloman at Swansea, Julian Steer in Cardiff, and then various others across the UK outside of Sustain as well, are looking at either waste products and how they might be able to use as supplements for anthracite and mined coal, but also a biogenic carbon as well. So the options to sustainably grow biochars in ways that actually remediate carbon from land use, as well as being able to as well as having a net benefit within the steelmaking process itself. And from the perspective of continuing to burn gas or produce CO2 through the EAF process, we also need to think about that other end of the carbon cycle, which is the emissions of the gases themselves. And that's some work that's been done here by Sheffield University. So this is a demonstrator that we've built through Sustain in a collaboration with AESC or Sheffield University. And this has been doing a tour of the UK steelmaking plants and being plugged. So this is the reheat furnace at Brinsworth, for example, being plugged into various different parts to look at the efficacy of this very low energy alternative to the current amine technologies for carbon capture or capture of those residual gases. And this has proved to be very successful. And this has been complemented by work both at Sheffield and at Swansea. So at Swansea, they're looking at electrolytic conversion through falling film electrolyzers, which are actually already quite well advanced in the chloroalkali production process, so can be scaled, and thermocatalytic conversion at Sheffield University as well, looking at producing new products. And we've been able to scale this pretty successfully, doing these plant trials, but also working with potential customers of these carbon products as well. So thinking about how steel can be part of the solution in terms of providing low CO2 work. And in Swansea, we've been funded by Coca-Cola to make bottle caps, which is a drop in the ocean, really, of course, but is an interesting way of looking at potentially establishing new supply chains using the gaseous products that come from steel making. And the last thing that I wanted to talk about from a technical perspective is raw materials. So that also sits on the steel strategy agenda. And those of us who've been thinking about this a lot will know that there's essentially one key alternative to the blast furnace, which is being touted at the moment, which is hydrogen DRI. Yes, there are other molten salt electrolysis and things like that, which are being discussed, but the primary one that's being looked at the moment is DRI. The interesting thing about DRI is, and this is some work that Jeff Brooks did in Swinburne University, is you look at as you start to increase the amount of DRI that you put into the mix within the EAF, you can start to approach the range of total emissions that might exist within the integrated steelmaking process. And so you need to take your choices very carefully about, well, what is your demand for DRI? I'm going to come to talk about the US case very briefly in a minute, because I appreciate we're starting to run out of time. The other thing that you need to think about there, not only how much DRI do you actually need to use and what the total demand is, but then also how much supply of DRI quality iron ore is there available to us that would be able to be used in a conventional shaft furnace. And that is actually relatively low. Interestingly, if you look at the proportions that are currently available and then you map them against the quantity of iron by volume that's actually being produced via DRI processes, they're approximately equivalent, around 3 to 5% year on year if you look at the world steel data. And I don't believe that to be a coincidence. So there's a significant challenge either for the beneficiation of the ore or for the processing of the material. There are ways that we can look at doing that, but then essentially you end up doing a decoupled blast furnace process. So you can do a solid state reduction with hydrogen of the ore itself, but then it would have relatively high gangue levels because of the core ore quality and low metallization rates, which means that you then have to do a liquid phase refinement in something like a submerged arc furnace. At that point, you're essentially just doing a blast furnace decoupled, and depending on how much of that you're going to use, then you have to ask yourself whether or not you're starting to impinge again back into this sort of range of potential outputs from integrated steelmaking. So this is quite a complex problem, and it's going to be mostly solved where we have availability of scrap material, which is a big question because there's a huge deficit globally against the demand for steel, on the quality of scrap that we're putting into the process. So the level of dilution that we're going to need as a function of the iron unit part of the raw material input is going to be a strong function of the quality of the scrap that we're actually producing. Now, if you look at the UK and you just do a basic inventory of the material that we've produced and consumed through imports within the UK, you can see that about 70% of it should be really, really low copper. And only a small fraction of it should be at higher levels of copper, which if you look at this diagram here, which is more suited to the levels of residuals for the US, this is a US derived diagram, I should say, then you can actually see that we should be able to produce the vast majority of materials from almost 100% scrap. And that would give us a huge carbon benefit as we have been able to calculate. But if you look at this in detail, we've gone out and looked at the different behavior of the scrap management processes in different jurisdictions across the world and pulled together what we're calling the international state of the art with regards to scrap processing. And what we found is, if you look at the UK compared to Western Europe, because they've been on this journey, and I alluded to this earlier on, within the UK, within the US for longer than we have here, about 30 years ahead of us, to be honest. They have been doing this sort of dilution at the minimum level per product specification. So rather than necessarily looking to the future and thinking, right, what happens at the third, fourth, fifth generation of materials that might be recycled as they come to the end of their life, they've been thinking, how do we hit the minimum residual level for this product now, this product now, this product now? And those decisions may have been taken 20 years ago. The problem is that as those materials now come to the end of their life, they're starting to get large, what we will call intrinsic contamination. So contamination that is actually, in this example, copper, but it could be any of those key elements that we want to avoid reintroducing into the supply chain. Any of those, that copper is actually now baked into the material, which means that their intrinsic or base load of copper within their arising scrap is now about twice that, if not more, than it is in the UK. That is one of the things that has resulted in a significant investment in scrap processing and vertical supply chain integration within the US of steelmakers and scrap companies as they seek to try to de-risk themselves from this. And the advantage that we have in the UK is that if we can use all of this knowledge through the grade development and the research that we're all doing collectively within the academic sphere, and we can match it with some of this available technology that we know exists with regards to best practice in scrap processing technology, then we will minimize our requirement to dilute our materials and still be able to produce those grades of very, very high quality. And I think this is where all of us within the academic sphere, working across a whole range of different areas, kind of have a role in coming together and demonstrating the art of the possible to those people who are going to be making the decisions as a function of the steel strategy within the UK about what we might be able to do to control those supply chains here in the UK and generate something which is genuinely competitive from a decarbonisation perspective. So here's a line that we set up in Swansea University, which we've been using to analyse different forms of scrap and image it as well. And we're collaborating with the guys in WMG at the moment on looking at modelling of the scrap flows and AI to potentially identify the composition of different amounts of scrap. And that's one piece of work that we're doing in collaboration with Zushu at Warwick. But another piece of work that we've done as part of an Innovate proposal is start to look at some different scenarios for different products and see what the effect of controlling that scrap supply chain might be on the eventual carbon footprint of the material. And if we take a sort of a base sort of 10% scrap input condition for say hot rolled coil, you can see how that might come down, steel plate, and so on and so on. So you can see that as a function of different product types, this careful control of the scrap content can have a significant effect. And I would also say that if we were able to relax some of the residuals by more robust design, then we would be able to boost these benefits even further. Particularly where we're approaching 100% scrap input. And this is basically on the basis of the fact that we're offsetting the input of pig iron produced through unabated blast furnace production. Of course, we might also be solving that problem from the perspective of hydrogen-based DRI or other smelting technologies. But my belief at the moment is that those will not have a significant contribution in the short term, and we are in a race against time with regards to the climate emergency. So if I revert back then, so those are some things to think about in terms of how you can contribute to the steel strategy and make it a success within the UK. And what is the missing but crucial ingredient that I spotted as a potential gap within the steel strategy? And the answer is you, all of you and all of us. I think people and the skills that they have are an incredibly important part of successfully delivering any steel strategy. Some inspiration that I take from this, these are not all of the ECRs that we funded, but this is just a slide that I had available to me. So apologize if you're actually one of these people on our ECR early career researcher platform, but don't see your name up in lights. We want to develop future leaders, and we've been quite successful at this, and I'm really proud of this activity where we're supporting these early career researchers to develop their own research independence and take forward their own research careers, working in collaboration with the steel industry. These people really are very, very important, and supporting them and connecting them through the development of their careers with the steel industry within the UK, but more broadly internationally as well, is going to be extremely important, and it's probably actually the critical factor in us being able to deliver a successful transformation to, again, I'll put it in inverted commas, green steel production within the UK. And just to give you an indication of what this means to people as individuals beyond some of the research outputs that they've been able to develop with this research funding is people like Pung, Stephen, and of course very familiar with in Warwick would be Frank. Stephen now, of course, formerly at WMG, then with us in Swansea and now Coventry. All of these three have gone on to take on roles as permanent academics, working now specifically with the steel industry, and that's something that I'm very proud of as an output of the programme of Sustain, but also very proud for them in terms of their continued commitment to this sector. One of the most exciting sectors that I think you can possibly work in. So, and this talent pipeline, I'm basically done now. This talent pipeline is extremely important. This is our own version of this from a project that we're running within South Wales, but I think it applies to many other areas. We really need to identify what these skills gaps are, and there are a series of European projects that are doing that. And we need to look at how we can make interventions at each stage of this ladder. And the more that we learn through our research about steel and advanced steel processing, the more we're going to be able to make interventions across there and really increase the skill base to deliver the transition successfully. So in summary, the UK is entering this period of significant change for the steel industry, and that's going to be underpinned by a UK strategy for steel. There is much research work that we still need to do, and there are some key themes that I've picked out here, but of course there are many more, but this is just for the purposes of motivation, if anything else, around sustainable metallurgy, the raw materials that we're using, those different vectors of energy and the decarbonisation, both the measurement of it, but also the technologies that we're looking to develop as well, that are going to be critical post the transition. And when I'm talking about transition there, I'm talking obviously primarily about Scunthorpe and the Port Talbot sites. And to me, the most important thing and my closing point is that you, as an individual, as much as the research that you're actually doing, are critical component to delivering this strategy. And I hope that I've gone some way to motivating you to getting involved in delivering this successfully within the UK. Thank you very much.
Thank you, Cameron, for a nice talk covering various themes of research you are doing under the Sustain Hub with the Sustain partners. And the floor is open for any questions. Yeah, Carl, please.
Carl.
Hey, Cam. Happy New Year.
Happy New Year.
Forgive me if this is a stupid question because it's only really come to my mind, or if it already happens. When we talk about recycling or circularity within steel, we talk about putting steel products back into steel making. Aluminium is infamous for being quite hard to recycle. Is there much in steel circularity where we take the scrap products of other materials? So obviously iron is a bad contaminant within the aluminium industry. We don't care about that. For us alloying aluminium into steels, do we take scrap aluminium at the moment? And are there other cases of that across the other alloying, or do we still really take ferroalloys as our mix? And therefore, at the moment, when we think about residuals, we think more about copper, tin, chrome, nickel. Should we be starting thinking about, I don't know, magnesium, something like that?
I hope I'm going to address your question correctly, but you do stop me if I'm sort of going off on a tangent that you weren't really looking for. So I'll try to pick off one of those at a time. I think the comparison with aluminium is really interesting because yes, it's difficult to particularly for thin section and formable aluminium materials, it's really difficult to manage. And of course, the work that's been going on at Brunel, they've been looking and within Aval, they've been looking at trying to do that successfully within the UK. But they have less grades to hit, and that in itself makes their life a little bit easier, yeah, than it does for us. So it's harder, yes, in one way at a very fundamental level, but slightly easier in terms of the number of different grades that they've got to make. And I think you make a really interesting point about, let's call it the other fraction of either material. So iron would be considered in the other fraction of an aluminium stream, and aluminium would be considered an other fraction in the steel stream. And I think we need to get a lot more holistic about how we manage those two different streams. We're trying to do that, I think, at a strategic level within the UK, so that, you know, the guys who are interested in consuming aluminium and the guys who are interested in consuming steel, in some cases, are the same people. So take JLR, for example. They're very interested in having clean, renewable sources of both aluminium and steel. And I think there's a lot that those companies can do to try to manage their supply chains of material, both the scrap that they produce on site before it gets to a customer, but also their management of, say, vehicles towards the end of life as well. But the other interesting one is actually copper, because the low levels of copper that exist within steel don't really make sense. You wouldn't see a copper smelter buying, you know, millions of tons of scrap to extract, you know, fractions of a % of copper. But if you look at the impetus now that exists within the steelmaking sector to remove copper, that actually represents significant value, because even the residual material that comes from that scrap processing has a significantly higher copper content than the ores that they're looking to mine. So I think it's basically about talking to each other as much as anything else. Yeah, that's really going to make the difference.
Yeah, and I think one of the last sustained ones really talks about the energy cost of the ferroalloys, and I think ferrovanadium was one of the very worst ones. And obviously vanadium is very heavily alloyed in titanium alloys, and I don't know how much has been done in terms, I don't really know what happens to titanium in terms of circularity of titanium. I'm assuming it's quite difficult, although the same argument is that there's less grades of titanium. But I don't know what that analysis is, and therefore, you know, that would have a different problem in that you've got a very specific titanium vanadium relationship that would come in, and then that would, if we were to use that into steel. I don't know. I just suddenly thinking that we're talking about steel recycling steel, but I don't know whether, you know, if you melt steel, you melt most other alloys. So just wondering.
You're picking some good examples, Carl, because one of my favorite facts in steelmaking, there's more titanium used in the steel industry than there is in the titanium industry. So I think you stumble on something that's really
same with vanadium. Same with vanadium as well. We think about vanadium, we only put like a pinch of vanadium in there. But, you know, and then you think of Ti-64, you know, surely you use more vanadium in titanium alloys. But, you know, speaking to Vanatec, you know, obviously their biggest customer is still the steel industry.
Yeah, it's not even close. So I think there are those opportunities. There's bits of work. So Will Robertson, to shout out to him at Sheffield University, has been doing, as a PhD student, has been doing some work with Liberty, looking at what he might be able to do to look to scavenge the scrap sources to offset the use of some of those ferroalloys, particularly those ones that either incur significant expense or significantly increase the carbon footprint of the materials that they're making. And we've done a little bit of work as well where we've pulled apart some of these scrap things, and then we've got students, undergraduate students in those cases actually, to come in, and I said, make me an AirMet 100. So just you go at this room full of scrap and see if you can make me an AirMet 100 from what you can find, just to see what the art of the possible might be with being able to displace the demand for some of those ferroalloys. So I think there's a significant opportunity to do that as well.
Great. Cheers, Cam. Appreciate it.
Thank you. Any other questions? One question I have, Cameron. In one of the scrap segregation slides, you mentioned you are using artificial intelligence methods to separate the scrap segregation. You're doing how much success you achieved so far? You think you using XRF method, or is it like laser-based methods? What type of methods?
Yeah, so the idea is really to build up kind of a knowledge base of the materials and how their composition might change as a function of their appearance. So in practical implementation, you could only ever really use an imaging technology that might be able to isolate different fractions that appear a certain way through simple imaging. There are, of course, XRF and LIBS methods and even X-ray methods that work on large volumes of scrap. You can imagine a huge amount of scrap running down a belt that might be a couple of meters wide. And then you can get kind of an aggregated chemistry, but it becomes difficult then to determine where that material is coming from. And of course, not everybody can look at that on a piece by piece basis. So what we're trying to do at the research stroke laboratory scale is to get a piece by piece understanding of the distributions of different types of materials, and then try to trace them back to their sources so that we might be able to work with different flows of material and start to identify ways of being able to separate them at source, which is of course the best way of being able to manage this. So I don't think the work that we're collectively doing is necessarily looking to replace a commercial scale. It may do, but at the moment we don't have ambitions necessarily to replace a commercial scale sorting or separation method, but more that we're looking at trying to use these methods to be able to get a more rapid determination of the sources and compositions of materials, which might help us to model the flows a little better, and then help the people who do have to make these investments in these separation technologies or have to develop policies with respect to export and import of scrap to make better decisions on either what they buy or what policies they implement.
Thank you. Any other questions from audience?
I just noticed Zushu's on the call, so he might be even better to answer that question than me, but or might want to comment. I don't know, because he's one of the people who's working on that. But
that's. I'm not sure he's okay. No problem. If no more further questions, I take this opportunity once again to thank Cameron for this wonderful talk, as well as for taking time in his busy schedule. Thank you all for joining, and have a wonderful afternoon or evening.